Hey everyone, so let's solve today's LeetCode POTD, two best non-overlapping events. So I will be discussing three approaches here. First will be using a DP with binary search, then using prefix max strategy with binary search, and then a very popular approach of line sweep algorithm. Now that algorithm is pretty important and is asked in interviews a lot. Recently it was asked to one of my friends in Google interviews. Okay, so let's means read the problem statement and we'll be discussing all the approaches step by step. So we are given a zero index 2D integer array of events where events of I is start time of I, end time of I, and there is a value associated with it. Now ith event start at this time, ends at this time, and if we attend this particular event, then we'll be receiving a value I. Now we can choose at most two non-overlapping events to attend such that the sum of their values is maximized. And now we need to return this maximum sum that we can get. And we are also given that the start time and end time is inclusive. That means we cannot attend a event as soon as we end a event at that particular time. So if we end a particular event at this particular time of suppose a to x, then we cannot start a new event from this time x. Okay, so this is what it is given. So if you attend at event with n time t, the next event must start at or after t plus 1. Okay, that means x plus 1. We are also given that the length of events can go up to 1e5 and the start and end time can go up to 1e9, and as well as value can go up to 1e6. So for example, if we have this as the events, so we are given times as 1 to 5. So let's try to plot it. So we have 1, 2, 3, 4, 5. Now from 1 to 3 we have a cost as value as 2. Then from 4 to 5 we again have a value of 2. And from 2 to 4 we have a value of 3. Now we can pick at most two events such that the sum of values of those two events is maximized. So obviously we see if we pick this event from 2 to 4, we'll not be able to pick any of these two events. So in this case the value will remain 3 only. But if we pick these two events, since they are non-overlapping, so hence we will be able to get a value of 2 plus 2 equals to 4, which will be the most optimal way here. Hence 4 is the maximum output here. Okay. Similarly, let's see another input. So again, we are given till 5. So let's see 1, 2, 3, 4, 5. The first event is from 1 to 3 and has a value 2. The second event is from 4 to 5 and has a value 2. And the first event is from 1 to 5 and has a value of 5. Now we see if we try to choose these two non-overlapping events, we will get a value of 2 plus 2 equals to 4. But if we simply choose this single event, we will be getting a value of 5. We will not be able to choose these two events, but we will get a value of 5. Hence, choosing 5 means choosing this event will be the most optimal, and the maximum value that we will be able to get is 5 here. Let's see another input. So we are given that we have from 1 till 6. So 1, 2, 3, 4, 5, 6. Now 1 to 5 we have two events. One is of value 3 and another one is of value 1. And from 6 to 6 means at this particular time only we have an event which has a value 5. So we'll obviously if we want to pick an event from between 1 to 5, we'll obviously be picking this event because it has a higher value. And we'll be able to pick this event as well because it is non-overlapping with this event. Since the total value that we'll be getting is 3 plus 5 equals to 8, which is the maximum possible here, and hence the output here is 8. Okay, so in this manner we'll be we are required to choose any two non-overlapping events such that the total sum of cost is a maximum. So what will be the most naive way of solving it, since we are required to choose at most two events? So for a single event will maintain the max of values, max value of I. And for two events, what we'll do, for two events, suppose we can iterate through means all possibilities of two events and see whether they are means overlapping or not. And if they are not, then I'll simply sum them. Okay, and update our global maximum. But we know the constraints can go up to 1e5. So obviously choosing these two events in a brute force manner in the order of n square will give us theory. So obviously we will not be following that approach. So what approach can be used? We know like we are required to choose at most two events, and now each event has a choice of either getting means picked up or not getting picked up, right? And we can only pick at most two events. So it is sure like means since each event has a choice of getting picked up or not getting picked up, maybe we can apply dynamic programming here. Okay, so let's see the first approach that we'll be using to solve it using dynamic programming. Plus we'll see like why binary search is required as well. Okay, so the first approach will be DP plus binary search using normal memoization. So now we decide for every event whether to pick it or skip it. Okay, so first we need to sort the events in some means either on the basis of endpoints or on the basis of start points, so that we are means traversing through the events in like increasing order of time based on like whether events get means completed earlier or not. Okay, so we'll sort the events based on their start times. Why? Because this will allow us to means process the events in the chronological order. Because suppose we have an event starting before, then we will not process some event which starts afterwards first. Okay, we'll process first this event, then we'll be processing this event. Okay, so at each index I, what we have? We have the choices of either picking this particular event or skipping it and moving on to the next event, right? So if at index I we have two choices. Skip, that means don't add an event I, so we'll simply move to I plus 1. But if we pick it, then we must attend event I, add its value, means attend this event, add its value, and now we need to move to such a event whose start point is after this point. That means it must start after this point. Okay, so since events cannot overlap, the next event that we must can attend must start after this I ends. Okay, so now once we are picking it, we need to find the next event which whose start time is greater than this end time, and then means move I to that particular index. Okay, so now if we try to means in a using a straightforward loop, if we try to find out this next event, then that will again cost us big of n, and the overall complexity will again become n square. Okay, so hence we need to find this next event optimally. So since we know like the events are already sorted in increasing order, now what do we want? We want to find the first index such that events of index comma 0, that means its start time is greater than the current end time that we have. That means events of, if we are at index I, so events of I comma 1. So we want to find this first index for this particular I such that this index means start time is greater than the current end time. So and we'll be like we have the choice of picking, means we have this I will be changing, right? Means picking can happen at every index. So what if we try to pre-compute this information using binary search? That is, for each I we try to pre-compute the next event, which will be means the next event which denotes like the first event on the right whose start time is greater than the current event end time. Okay, so if you simply pre-compute this information, then we'll simply move I to what? To next of I. Okay, where next of I stores the index which means whose start time is greater than the current index end time. So that's why we have used a binary search here. What you'll do, instead of linearly searching for the next available event, we pre-compute a next array using binary search. Now for every event I, next of I stores the index of the first event j, where start time of j is greater than end time of I. And now if we have this means next of I, will simply means when we are picking it, we'll simply update I with next of I, so that we do not need to means linearly iterate and find the next available. Okay, so using these two approaches, we'll be like able to solve the problem. So let's see the DP state that we'll be using. So DP state will be simply n cross 3, because 3 means count denotes the number of events that we have already picked. So this will be either 0, 1 or 2. We cannot pick more than 2. And this n denotes the means will be the index that we are currently on. Okay, so DP of index count stores the maximum value achievable starting from this index and having already picked up count elements. So what will be the base case here? When this index reaches n, means no events left, or the count that we have has become 2. That means we will not be able to pick any more events. So we'll simply return 0 in this case. Now let's see the transitions that will be happening. So in the case of pick, what you'll do, we'll simply add the value is present at index 0 for events of index. So we'll add this value, current value, and now since we have picked it, so we need to jump to the next index. Okay, so we'll jump to this index which we have already pre-computed using normal binary search, and we'll increase our count. And in the skip case, what we'll do, we'll simply ignore the current value and move to index I plus 1 with the same count. Okay, so this is how we'll be approaching this problem. And now how do we pre-compute this using binary search? So simply, if we are at a particular I, then the available ranges, means the range of binary search is from I plus 1 till n minus 1. These are the range of indices. So we want to find the first mid such that events of mid comma 0 is greater than events of I comma 1. So we'll find this leftmost mid. So if this condition is satisfied on mid, we'll simply do what? We'll update mid, means we'll update our answer with this mid, and we want to find the leftmost. So we'll update our high, means move high to the left. Okay, and at each step, if this condition is not satisfied, so we'll move low to the right, so that we want an event which is lying far on the right, so that this condition is satisfied. Okay, so in this simple manner, we'll be like doing binary search, and we'll be able to do this. And initially the range will be simply low will be pointing here and high will be pointing here. So we'll be able to do this pre-computation in n of means, and in the end we'll simply, after we have executed binary search, next of I will simply become this answer that we have calculated. Okay, so in this manner we'll be able to do the, means first we are sorting it, so it will be taking n log n, then we are pre-computing this next array which will also take overall n log n, and then this dp state will be taking big of n to compute n into 3. So this will be like the first approach that will be using to solve it. Let's try to see the code, then the approach will become much clearer in your head. So what you'll do, we initially has these events, we'll simply sort it on the basis of start times. Now we initialize the dp. Now we need to do pre-computations for the next array. So for each I, the range will be from I plus 1 till n minus 1, and we have the mid and initially initialize the answer as n, so that n denotes that, means there exists no event on the right whose start time is greater than current send time. Now we'll iterate, means do the binary search. If the current events mid, means start time, is greater than n time, we'll update our answer this mid, and means move the search space to the towards the left. Else we will move the search space towards the right, and once this binary search has been executed, this answer will be storing the next index. So we'll simply update next of I with this answer. Now we want to find, means calculate the dp. So what we will calling it, initially the index is 0 and the count as well is initially 0. Now we simply call this memo function with these values. So as soon as index becomes n or count is already 2, we'll simply return 0, or if the state has already been calculated, we'll simply return it. Now there are two cases, either to pick it or skip it. When you pick it, we'll add the current value and move the index to the next of index. Move this index to the next of index and simply increase our count. And since we have reached this point, we know like count is not equals to 2, means count is less than 2. Then only we'll be picking it. Okay, and else if we are skipping it, then index moves to index plus 1 and count remains the same only. And at each step we'll be taking the maximum of both, so that we are getting the maximum value possible. So in this manner we will be able to do, means calculate the entire values in the overall complexity of n log n, and the space that we have used is of the order of n. Okay, so let's try to submit this code here and see. This is the same code that we tried to submit. Let's try to submit it again and see how much time it takes to run. It runs in like beats only 30% of the solution because of the like recursive stack space that we'll be creating. Okay, so what can we, means this approach is also fine. Maybe we can convert it into tabulation as well, then space optimization tabulation as well. And no, space optimization will not be possible because we see like this index is dependent on like random values. Okay, so we'll be able to write the tabulation here. So this approach is pretty good, right? But can we do it without using DP? So yes, we can. We can like try to maintain, for suppose if we are at a particular event I, suppose if we are picking this particular event, then we can maintain in a prefix what will be the maximum value of any event which has occurred before this event. So if we are picking this particular event, we can add its value and the maximum value that we have stored so far. Okay, so we can find out these two values and simply add to our current event if we are picking this particular event. So this kind of approach we can use using prefix max plus applying binary search additive step to solve. So let's see this approach now. So what you'll do, this approach iterates through the events, and for each event ask, if I treat this event as my second event, what is the best first event that I could have picked that doesn't overlap? That means if I am picking this particular event I want to find some event j less than I, such that means the prefix, it will be the event which has the maximum value so far, means all out of all the events this event has a maximum value. So the entire value will become this value plus this maximum value that we have stored. Okay, so using this prefix max plus binary set we will be able to do that. So how will be like sorting this means sorting what will be the sorting strategy in this case? What do we want? When we are at a particular event I, we want to find all the events whose end times are before this particular I. Okay, so hence we need to sort it on the, not on the basis of a start time. Suppose this is a start times. So if we are at particular event I, will not be, means this event has or not already ended, right? So hence we want to sort it on the basis of end times. Okay, so that when we are at a particular event I, we'll only account those events whose end times are before the current start times. Okay, so if we sort it normally on the basis of start times, so we see like its start time is before this, but means it has not yet completed. So we want to only means store prefix for those indices or events whose means who have already been completed. So hence we will be sorting it on the basis of endpoints. Okay, so here you sort events by end time. This is crucial because it ensures that as we iterate through the array, any event at index j less than I which will be finishing before or at the same time as event I. Okay, now we compute this prefix max array which will be storing the maximum single value found among all events from index 0 to I. Okay, so suppose if we are at in any index I, we will be able to get this, means just finding the we'll just simply find the rightmost index whose end time is less than the current start time, and then that prefix value will be means correct accounting. So what means the strategy for any current event I, we want to find a previous event that ended strictly before events of I started. So how will we finding that? Since it is sorted on the end time, so we'll simply use binary search to find the rightmost index whose end time is less than current events start time. Okay, once we have this, what we'll do, if this is the index, then prefix of index will be storing the maximum value that we have for all events from 0 till this particular index. Okay, so we'll be accounting that as well as the value obtainable from the current event. Okay, so this is how we'll be solving it and we'll be able to get the result. So I hope the approach is clear. The binary search will be same in this case. For I, the range will be from 0 to I minus 1. Okay, and then means the range will be like this, and then we'll be applying binary search to find the rightmost index. Yeah, means in previous approach we tried to find the leftmost index. In this case we will be finding the rightmost index. Okay, so let's try to see this approach as well here. Means without using DP, how we are going to solve it. So without DP we'll be using prefix max plus binary search. So we'll be first sorting it on the basis of endpoints. So this is how we'll be writing the custom comparator. If the endpoints are equal, we'll be sorting it on the basis of start points, but if they are not, then we'll simply sort it on the basis of endpoints. Now we create this prefix vector. This maxi will be storing the final answer. Okay, final answer means the maximum value that we can get. Now we iterate through each event, means this is the second event that we'll be picking. So we need to find the last index with events of index comma 1 less than, means its end time is less than current event start time. So the search space is simply from 0 to I minus 1, and we have initialized this index with minus 1. Means if this remains minus 1, that means there exists no event on the left. Now we simply do the binary search. If this condition is satisfied, we'll update our index min width and move the search space to the right because we want to find the last index, and else we will move the search space towards the left so that we are able to satisfy this condition. Now if this index has not become, means if we have got some value mid, then that means we have got some index. So we simply update our final answer with max of final answer comma the prefix of index, that means the maximum value that we have got till this index plus the current events value. okay, which is stored at event cycle. And else if it's equals to -1, then we'll simply have this value only. Okay, we'll not be having any left event to choose. So hence in this case we'll be updating our maxi with this value only. And now since we are moving from I to I plus 1, we need to update the prefix of I. The prefix of I will be simply updated with prefix of max of prefix of I comma prefix of I minus 1, where prefix of I is events of I. And then we'll be simply returning this maxi. So now we have saw like we avoided the complex DP approach of picking and non-picking. We simply sorted it on the basis of endpoints, and then we are able to like solve this problem. So the complexity still remains of the order of n log n, and we have used like a big of n space here as well. So space and complexity remains the same, but this is another way of solving it. Means we are trying to explore all possibilities of solving it. Means suppose interviewer asked to like do not go into such complexity of picking or not picking, simply like use binary search or something of the prefix match, and avoid DP if someone asks you to do so. How will be using? Okay, so this is the approach that we'll be using. Let's try to like see, means let's try to submit this code as well here and see how much time it takes to run. Currently it beats means 30% of the solution, and the DP one beated around 26% of the solution, I think. Let's try to see how much time it runs in 75 fms and beats 68% of the solution. Okay, and the space is beaten mostly because like in DP we would have the means the recursive space as well. So these were the two approaches discussed, which is like a pretty popular. But the next approach that we are going to discuss is the line sweep algorithm, which is really important. As I already told you, like it was asked in Google interviews as well recently, so it is pretty important. So let's see that approach. What is a line sweep algorithm and how do we use it in the case of like a 2D events array? Whenever we are given like 2D data, how do we convert that into 1D data and then simply process it means normally, okay, using a line sweep kind of thing. So let's try to see the approach of line sweep, then it will become much clearer how this approach will be working. So this approach flattens the 2D intervals that we are given into a 1D timeline of points. Okay, so currently we are given start time Si and end time, right? But we will be converting it into a 1D array. Okay, we will be converting it into a 1D form, and then process this on the basis of whether if it is Si, then it should be having a flag as true, means this is a start point, and if it is Ei, then it will be simply means as false. So we'll be simply iterating through the timelines, okay, the times that we have. Okay, instead of these Si and I, will be iterating through times, and if this is a start time, we'll be giving it a value true, and if it is the end time, then we'll be giving it as a value false, and then we'll be iterating through from the start to the end. Okay, so this is the approach that we use in binary means a normal line sweep. Let's try to see it in detail. So what you'll do, every event has two critical moments, when it starts and when it ends. So we'll distinguish means both of them by assigning separate flag variables for them. So we, for the start time, what we'll have the type as start, and the value means will have its own value, means the value remains the same for start as well as endpoint. And it will be ending, means it will be from Si till Ei. So at Ei plus 1, this point, this event will be getting ended. So at Ei plus 1, this is getting event ended. So will type means its type will be end and the value remains the same. Now why are we using end time plus 1 and not end time? Because the events that we are given are inclusive, right? We cannot start a new event as soon as we end here. Okay, so we have made it I plus 1 so that we are only starting new events from this point. Okay, not from this point. So that's why we have used Ei plus 1 instead of Ei. So what we'll do, we have like if the times of means are equal, so we'll assign true values and false values. So what do we want, since Ei plus 1 will have the false value, so we want to means this event to get processed first, then only means if at Ei plus 1 we have some true value to get means we have some Si which will having true value to get started. Okay, so if times are equal, who will be coming first? So since false means false comes before true, so obviously this value will be getting processed first and then this Si will be getting processed. So that's why we have assigned 0 and 1. Okay, so now if an event ends at T, which will be stored as t plus 1 type false. So another event which starts at t plus 1 which will be stored at t plus 1 and type true. So this end event will be stored, means processed first, then this event will be processed. Okay, now how do we once we have created these separate vectors based on the time, how will we sweeping across? So we'll be maintaining two values. Max value will be storing the maximum value of any event that has completed finishing so far. So that means based on the number of false that we have encountered, okay, number of false that we have encountered, we'll be updating this max value. So suppose we are at a particular time and the current event means is of type true. So that means it is the start of some value. Okay, so you can update the maximum answer that we will be getting as its value that we are currently have, value I suppose, and this max value will be storing the, suppose we had got some false events here. That means these 4 events has been ended before. So will be this max value will be storing the maximum value of all these events. So this max value plus the current value that we have will simply means summing them and to get the maximum result. Okay, so in this means whenever we hit a start point, we calculate the current event value plus this max value, okay, to update our maximum answer. So this is how we, instead of using a 2D means 2D intervals, we are converting it into a 1D timeline of points and then processing them in order. This is pretty important. There are multiple problems, such as you can try to solve suppose a rectangle area 2. This was the problem which was asked in a Google interview, and this line sweep algorithm was expected. So part 1 as well as part 2. So they asked first they asked this rectangle area part 1, and then they were expecting this line sweep algorithm as well as a part of the discussion. Okay, so if you are already aware of it, this is a plus. That's why we are discussing all possible approaches. So let's try to see this code for this approach and then see how we are going to implement it. So this is the simple line sweep algorithm. We'll treat each point as a point, treat each time as a point, distinguish end or end start points using a flag variable. So this is the start time, and means this is the time that we'll be having, and this will be either true or false, and this will be denoting the value. So the L, R and value have it. So for each line we'll be pushing the L as true and the value, and R plus 1 means end time plus 1 as false and the value remains the same. Okay, now we'll simply sort it so that we are processing time, means processing the events on the basis of increasing time. Now we'll maintain this max values, which will be storing the maximum values of all the events that have been concluded so far, and this maxi will be storing the maximum answer that we are able to get. So the current time is simply id dot first, the value is id dot second, and start. So if start is true, that means current is the start of some event. So we'll be updating this maxi answer with the current value that we having plus the maximum value that we have got so far. So starting point, hence update our maximum answer. And if it is not the starting point, means if it is the ending point, that means we need to update this max value, because some event is getting ended here. Since we'll be updating our max value with the value present in this for this event. So we'll be updating our max value with max of max value comma value. So endpoint, hence we update maximum value so far for next events, and in the end we'll simply return this maxi value. So this is means the compact code of writing the line sweep algorithm. This can be extended to a lot of problems, and it is a pretty popular approach, and we should be aware about it. So let's try to submit this code as well here and see, means this is the same code that we discussed. Let's try to submit it and see how much time it takes to run. Initially it beats 68% of the solution, and now it we are sorting it currently, and it has a lot of value, so it may not run as much as fast as the prefix max plus binary search approach, but it is, means this approach is important. So I hope you were able to follow along with all the approaches that we tried to discuss today. First we started with DP with binary search, then prefix max plus binary search, and then means taking inference from this prefix max only, we try to means pre-compute this max well based on 1D points. Okay, so the line sweep algorithm I hope is also clear. So this was the means overall discussion of this problem. I hope you were able to follow along, and if you did, make sure to like as well as subscribe, and if you yet have any doubts remaining, make sure to comment down. I will be happy to respond. Thank you so much for watching.